Okay. I know you guys are excited. Here we go. When a force acts upon an object to cause a displacement. Can we think of that? Is that easy to picture? Is it better with the lights off? Better? Okay. So when a force acts upon an object to cause a displacement, could I do that? What about with this box? Could I put a force on this box and move it? All right. So we can visualize that, right? Okay. So we're going to give you a definition. It is said, the force that is, it is said that work was done upon the object. Okay, so what two things do you need to do work? A force and a displacement. Okay, and you'll find that that is the formula. Okay. Okay, so in order for a force to qualify as having done work, on an object, there must be a force. No. There must be a displacement. So you can highlight these keywords. And more importantly, the force must cause the displacement. Okay, so let's think of some examples and some non-examples. Anybody want to generate an example? Push a brick wall. Push a brick wall. Is that an example or a non-example? What am I doing? I'm applying a force, but I'm not causing a displacement. So I'm not accomplishing any work, even though I'm working hard. Right? So kind of like a different example. Real life example, work, and then your physics example. So that's a very good non-example. Let's get back to the pen. Okay, so non-example. Push a wall. I love that. And then how about some example? Kicking a soccer ball. As an example, kick a ball. Kick a ball. I happen to have a soccer ball. What happened? I applied a force, and the ball was displaced. Good. Any others? Can we relate back to some to the dynamics unit? What happens if I lift the ball off the ground? Did I do some work? Sure. if I pick up the ball and then put it back. So force, like the network. Yeah, you could think of it like that, network. Now if I drop the ball, what force does the work on the gravity? Good. So if I lift the ball, who does the force? If I drop the ball, what does the force? Gravity. Good. Question. Yeah. Because gravity, well, the force due to gravity, so the weight, yep. And the displacement. Good. Yeah, good. What about a rocket accelerating through space? Is there work being done there? A rocket accelerating through space. Is there work being done? Why? So the applied force, good. So a rocket accelerating through space. The force of the jet propulsion causes the displacement. Okay, good. What about a book falling off a table? What about this meter stick falling off the table? Was work done? Was it? Which force caused the displacement? Well, me just dropping it. What force causes the displacement? Gravity. Okay, good. What about a waiter carrying a tray above his head across the room at a constant velocity? Okay, so there's work for me to lift it above my head, yeah? Okay, so after that, once it's up there, and I move at a constant velocity, is there work being done on the ball? But I'm moving at a constant velocity. Work done on the ball. So you're saying I'm applying a force to go this way? Yeah, I like that. Initial force just to get started. Then you're moving at a constant velocity. That's Newton's first law, right? Good. Yeah, there's no work done on the ball. Like, the force wants to push down, right? And you're pushing up. And I'm moving this way. So, like, the initial force to get going this way is perpendicular to the force holding it up. Yeah, that's Newton's first law. Yeah. Okay. Yeah, kind of. Let's talk about some scenarios. Let's quantify the direction and the force and the displacement directions. Let me just change the background. Okay, let's talk about 3 scenarios, okay? Scenario A. Force and displacement in the same direction. Work being done? Yeah. And the angle, what's the angle between the force and the displacement? 0. Let's talk about scenario B. Force in one direction and the displacement in the other. What's going to happen here? So you think of it as like negative work?
Or I guess you kind of imagine like, say you're on a hill, and the box is coming down, and then you're trying to push the box up, but the box is still coming down. It's pushing you back to you. Maybe.
Yeah, or just basically stopping, a car stopping, right? You're driving one way and you're stopping. And let's think about another scenario. This is the waiter. What if the force points up, but the displacement is to the right? What's the angle between the force and the displacement here? 90. So I need to give you an equation. What's the equation on your chapter 5? What's it say? Work equals, what does it say on there? Work equals force times displacement. But it's missing one thing actually on your page. Cos theta. There's an extra term. This is the proper formula for work. Work equals force times distance times cos theta. Basic trigonometry lesson. If you've taken Math 20-1, this is going to be very basic for you. If you haven't taken Math 20-1, I feel bad for you. CAS rule. What's the CAS rule? Add sugar to coffee. And we're only going to focus on the top two quadrants. What's the value of cosine in the first quadrant? Positive. What's the value of cosine in the second quadrant? Okay, so with this extra term, with our work, we can see that work will actually have a positive and a negative sense. You can do positive work, you can do negative work. Scenario A, positive work or negative work? Scenario B, positive work or negative work? Good. And scenario C, this is where it gets dicey. Does anybody know cosine 90? 0. Cosine 90 is 0. So for scenario C, are you doing any work? Good. So there's no work in scenario C because the force vector and the displacement vector are perpendicular. Okay. Like for scenario A, you could also have this situation. What if the force vector was like at an angle, but the displacement was to the right? What would you do in that situation? This is like you got the dog on the chain and he doesn't want to walk, but you're pulling him. So, yeah. Go for it. What happens in this situation when the force is at an angle? Yeah, you use cosine theta, and what is that giving you? Yeah, go get it. Yeah, you're using which component? Right? If your displacement is to the right, but you're pulling up at an angle, you can only use the x component of the displacement. Okay? And we'll come to realize that it's always going to be like this. So, it's always going to be like this. So, the angle between the force and the displacement, that's what you're looking for. The angle between the force and the displacement. And this is the formula that we're going to use. Okay? Sorry, zoom back to that. You need that top thing? Okay, so you can add this in here next to your formula where theta is angle between force and displacement. Okay, let's put some notes on scenario B. Let's write down some notes for scenario B here. The force hinders. Do you guys know that word? Hinders? What does the force hinder mean? Adds or subtracts? Yeah, the force hinders the displacement rather than causing it. So what can you say there? You can call it negative work. What's one force that you can think of right now that hinders the displacement? Say that again. Car coming to a stop. Which force is that? The friction between the road and the tires. So I'm headed this way. You guys ever rollerblade before? You know those crazy stoppers on the... You're like rollerblading and then you put your heel up and it stops like this? You ever do that? Same idea. You're going that way and you're stopping, so the force is opposite. So say the rubber stopper, the frictional force is doing negative work, okay, to slow you down. Okay, so that's scenario B. And obviously scenario A, call that positive work, where the force causes the displacement, positive work. Okay? And for this example up here, where you're at an angle, this is like Fido on the chain. So you can put a little note here. Your dog Fido. Only the horizontal component does work on the horizontal displacement. So that's like the wagon, the lawnmower. Do you guys remember those problems? The wagon problem and the lawnmower problem? So I'm pushing the lawnmower, mowing the grass. Am I doing work? I'm doing work, right? And which component is doing the work? The x component or the y component? Because think about the displacement. I'm moving, so I just move this way. Yeah, it's the x. Okay? And does anybody know the unit for work? How do you guys know this? Science 10? The unit for work is the... Sorry, my screen's doing some funky things today. Is the joule. And the joule, if we break it down into the force unit and the displacement unit, what's the unit for force? What is it? The Newton meter. The Newton meter. And what's a Newton? What's a force? MA, right? So we got mg kilogram. Oh, why do I have mg in there? It's confusing you guys. So mass is kg. Oh, my screen is glitching hard. Whoa. So, no, it's glitching. So my Wi-Fi went down. Okay, so just erase this stuff in black. And we'll just call it the Newton meter. And if you want to do it on the board, we can do it on the board. So the Newton meter, the unit for Newton force, so mass times acceleration, kg meter per second squared times a meter. So it's like kg m squared per second square in fundamental units. And I'm not sure what my screen is doing. I've lost Wi-Fi. Okay, so let's go old school. That's enough for the notes for today. Okay. Oh, it's back. It's back. Yeah, let's just do 3 examples and then I'll assign some work, okay? And then we might bring it back for some more in a little bit here, because that's a short lesson. Now that my screen is working again. Let me just get it up there. Okay, so 3 examples for the 3 scenarios, okay? So back to like scenario A, B, and C. We have a 15 kilogram mass, and we'll say there's an applied force for whatever reason, 100 newtons, and the displacement is 5 meters to the right. And we can see that the force is also to the right. So how would we go and calculate work for this situation? What's the formula for work? Okay, so can somebody, Emmanuel, what's the force? 100 newtons. Zach, what's the displacement? Good. And Ethan, what is the angle between the force and the displacement? 0. Good. So you can put cosine 0. And I know that some of you are saying, well, Lineweber, cosine 0 is 1. Do I need to write that? I would recommend that you do put it, just to get in the habit, just to remind you. If you're very apt and you know you're not going to make a mistake, then fine, don't put cos theta. But I would recommend for most of you, just put cos theta, and then you can see that the angle between the force and the displacement is 0. And make sure you're in degree mode, right? Everybody go ahead and check cosine 0 right now. What is cosine 0? Check it. It better say 1, okay? So this is 100 times 5 times 1, 500 joules. Now, is work a vector or a scalar? Work is a vector or a scalar? Yeah, so you would think it's a vector because it's using two vectors to do it, but work is a scalar. It's a scalar quantity. It's just a number. You can't attach like a direction to the work. Okay, so work is going to be fully described by a single value, a single numerical value. So it's a scalar unit. However, you can have positive and negative work. So even though it's scalar, it can be both positive and negative. Okay? Another situation. This time we're pulling Fido by his chain. Okay? Poor Fido. Again, the force is 100 newtons, but it's going to be 30 degrees north of east. And the displacement is 5 meters to the right. Okay? So again, jump into your equation. Force times distance times cos theta. Help me out. Alan, what's the force? What's the force, Alan? Don't know it? Reyes. Oh, he's got it. 100. Reyes, what's the displacement? 5. Good. And Jacqueline, what's the angle between the force and the displacement? So you put cos 30 here. Cos 30, what is that, like 0.866 or something? Times 500. So is that 433 joules? All right. And one more. It's the scenario C. It's the waiter. So there's an upward force, 100 newtons. Why did I put that bracket? 100 newtons up. That must be what? The weight of the tray and the food on top of it. 100 newtons up. That's the force. The displacement is 5 meters to the right. He's just going to the table. He's going to the table 5 meters to the right. The force is upward. He's moving at a constant velocity. So the net force is 0 to the right. And there's no force causing this displacement to the right. No net force. Okay? So what's the work done?
Cos 90 is 0. 100 times 5 times 0 is 0.
100, 5, and cos 90. 0. Okay, page 167. Oh, actually, there's one more thing I gotta add to the notes. My bad. There's one more thing. It's quick though. This is force versus displacement graph. Okay, so physics 20, we're thinking about forces and displacements. Usually, thinking like 9 times out of 10, the force is constant. There's a constant force. So what you can do is you can just draw your constant force. Okay, and let's say there was some position change. There's some displacement change. So let's say this is x1 and x2. What we can do is we can shade underneath the graph. And you guys have seen this before with velocity time graphs. Okay, so what can you make a generalization here? On a graph of a force versus displacement. The area under the graph gives the work, right? Because what would happen for this rectangle? What's the length of this rectangle? And what's the width? The force times displacement. That's your work done. Okay? So let's jot that down. And then you're done for notes for today. Okay, so on a graph of force versus displacement, the total work done by the force is the area under the curve. And for the most part in physics 20, it won't be a curve, it'll just be a straight line. And then when you get to math 31, you'll understand that this is the integral, but that's calculus. So right now you're just going to assume that the work is the area under the curve, and usually it's straight line. Okay, and just put it between the initial and final positions, and that's it. Okay, so jump into page 167. And if you want, you can also read the summarizing notes that lead up to it. And Yes, there is a lot in this section. A lot of homework. So right now I want you to try to get to 14. 1 to 14 right now. So page 167, 1 to 14. Sorry, 163. You guys good with the notes or still keep it up there? Okay. Just Alan. Alan, can you see? Is it okay if you borrow from somebody for the rest of that? Do you have glasses normally? Okay, so just loading up the page 167 here, and I just want to show you a couple of the examples, and then I'll let you work. Give me 2 minutes, then you go. Okay, so let's take a look at the workbook, how they're doing their work, okay? Work is done against friction as a book is pushed 50 centimeters across the desk by a constant horizontal force. Calculate the work. While work is FD times cos theta. So how come they don't have that? Yeah, because it's 0. And remember that cosine 0 is 1. Okay, so they're omitting this times by 1. I recommend that you put it in. Okay? Question 2 just looks like there's some kinematics in there. So it looks like they're finding some acceleration first, and then some displacement, and then they find the work. So you can look at that. There's nothing really special about that, except what do you see here? Well, kilojoules for sure. And in question 1, it was in centimeters for sure. You got to make sure you're mindful of your units, absolutely. But there's some negative work. So it says net work is done by friction. Okay. So what does it say? To change the velocity of an 8-kilogram wagon as it moves along. Okay, so we know that friction is in the opposite direction of the displacement. So you're headed that way, and I'll use red for the friction, but friction is this way. So what is the angle between the force and the displacement? What's the angle here? 180. And what's cos 180? Type in cos 180. What do you get? Cos 180 should be -1. So that's why they have in here this -60. Myself personally, I would have done 60 times the 15 times cos 180. That's what I would have done. Yeah, we'll give you the negative answer. Okay. Three, we talked about 3. That was one of the non-examples. And 4, I don't like that they're showing 4 already. I don't like that at all. They're giving it away. So, what is mg? Put a bracket around mg. What is mg? Force of gravity. And what is h? Height, which is displacement. So it's still force times gravity. Do you guys recognize mgh? From Science 10, what is that? mgh. That's potential energy. Yeah, do you guys remember that? Potential energy, kinetic energy. Got a skier at the top of a hill. He skis down. All of his energy is converted to kinetic. Remember all that? Yeah. So right now it's giving it away that there is a link between work and energy. Okay. And we're going to talk more about that in later days. Okay. Let's jump to 5. Let's jump to 5. Let's take a look at what they're doing. For each situation below, identify the forces doing work, determine the work done by each force, and then determine the net work. Interesting, net work. Remember, force or net work is a scalar, so let's try to think about this. Example I, object is accelerating to the right. So what does that mean? The forces are balanced or unbalanced? And in which direction? There should be more to the right. If it's accelerating to the right, this force vector should be larger than, so that this makes sense, right? What about the up-down forces? What are they doing? Are they balanced? Yeah, it's not accelerating up into the air or down into the ground, right? Okay, so I'll use my pointer instead of my hand. This negative 40 joules, where are they getting that from? The displacement is 1 meter. What is this negative 40 joules? Is that the work done by which force? Friction. And the work done by the applied force. And then you can see here a net force calculation with, look at this. They figure out F net, 50, and then the work, the net work, is the net force times the 1 meter. So make a little note here. W net, use F net. Okay? And these are the work done by the forces separately. Work done by separate forces. And then they combine it here. You can also take a look at example 2. This looks like an object accelerating down. Just the force vector down is much larger than the force vector up. So what's the net force? 90 minus 60 is 30 down. I would just jump into that. I wouldn't even find out these work values. I would find the net force, the displacement, and I would calculate the work in that sense. Okay, so if you typically want to go with net work, net force, that's usually the way to go. But you can find them out separately. I think that's enough to get you guys started. 1 to 14, okay? Okay, have at her.